Thank you very much. Thank you for the possibility to speak here. It's my first time in Deligne, and it's a pleasure to be here. So I'm going to report on joint work with Liz Milicevic and Anne Thomas on affine Deligne Lusztig varieties. So we introduced some new combinatorial geometric methods to study these objects, and this is what I'm going to show you today. So, but before we formally introduce what affine Deligne Lusztig varieties are, just let me put it like this for a second. I'll abbreviate it by ADLV because it's so long to say. And they're a family of subvarieties of the affine flag variety. And they're indexed by a pair of elements. So these varieties, they're called X, X of B. And this pair XB, which lives inside the affine while group, times the group G you're looking at. And in the case of affine Deligne Lusztig varieties, this will be FQ bar Laurent series in T. Okay, so we have this family of varieties which we want to study, and in order to do so, we first need some combinatorics and geometry. So this is why I'm going to start with Coxeter groups and Coxeter complexes. So let's review what this is. I'll just give you the definition. A Coxeter group is a reflection group, and it just can be given by the following presentation. So you can write W with a set of generators, and it has relations of the form S times T to the MST is 1 for all pairs S and T in your set of generators, capital S. And these MST, they have to follow a bunch of rules. So first of all, if you put the same index, you get a 1. Then they're symmetric, MST equals MTS. And if there's no relation, we write MST to be infinity. So if the pair is of infinite order, no relation for ST. Okay, so associated to a group like this, there is a complex. So sigma depends on W, but also on the generating set S you pick. This is the Coxeter complex. And it's a simplicial complex, so you can view it as a partially ordered set. And as a partially ordered set, it is just the, so it is as a partially ordered set, the set of special cosets. Now I'm lacking the right words. It's the standard cosets. Okay, let me write it down. It's the poset of standard cosets. Oh my goodness. Poset of standard cosets. Okay, we'll see examples in a second, but let me just put down the definition first. So it's things like little w times capital W indexed by j, where this little w is just an element of your group, and this j is some subset of your generating set. And I don't allow it to be equal to S, but I will allow it to be equal to the empty set. Okay, so a simplex in the simplicial complex then corresponds to an element in this poset. And they're ordered by reverse inclusion. So the smallest simplex is the biggest element. Biggest. Okay, so examples. If we look at the very easy examples, so there's just one generator, and the only condition we then need to impose is that its square is the identity. Okay, so we get a very easy reflection group. It contains two elements, namely the identity and S. But I can also view this as a coset of W empty set, okay? And I can view the element S as S times W, the empty set. So here what you see is the Coxeter complex associated to this group, okay? Let's make it a little bit more interesting. Take two generators at an angle of 60 degrees, ST. This corresponds to picking for W. Well, of course, we have to put S squared equals T squared equals 1. And the 60 degree here corresponds to S times T having order 3. So the power 3 equals 1. Okay, so what we get is 3 reflections in total. And as a complex, we will see a tiled S1. Let me just draw it. Here, I said the simplices, they should correspond to elements in this poset of cosets. The big ones, the biggest simplices, they're edges here, okay? So they're labeled by the smallest guys. So the smallest guys are, again, the cosets of W empty set. So they're just labeled by the elements of W itself. So we start by labeling with the identity up here. Then we get label T on the right-hand side, S here, then T times S on the bottom right, S times T here, and down here we just have the longest word in W, which is STS, or equivalently TST. So the vertices, they're smaller in this reverse order. So for example, here, what you see is precisely the stabilizer of this point in the action of W on this sphere. So it's W indexed by the set containing T. Up here we see W indexed by the set containing S. And any other vertex of the same color, namely white here and black here, is a coset of the same W index J. Okay, so this guy down here, what is it? It should be S times T W S. And this here, it's obtained from a reflection along T from this vertex. So yeah, you can continue. Sorry, this one is the reflection along T of this vertex. So you can label this by T times W index S. And you can continue and fill out the rest. Okay. So these examples, they're spherical. They're called spherical because they produce as a Coxeter complex a tiled sphere. Okay, so you can realize them as reflection groups on a sphere. And I'll show you 2 more examples. For space reasons, let me put it like this. Take the real line and take alternating types of black and white vertices. And again, well, you can view the vertices as hyperplanes, so you can reflect along them. So there's a reflection S. Let's put the S here along a white vertex. And a reflection T along a black vertex, and a reflection T along a white vertex. So the group S and T generate W is, well, generated by S and T. Both of them are reflections, so of order 2, and then there's no relation among them other than that, right? So we put S times T to the infinity is 1 to stick with our convention from up there. Okay, what you see is that this W up here, where I put a little 0 on the bottom, sits inside this W I've written here as the stabilizer of a point. So it's exactly, and the embedding is just given by put S, this S to this S, okay? So you see this as a subgroup. And again, you can label your simplices. So the maximal simplices are edges. We have the identity here, T here, S here. And then this would be S times T, and so on, okay? Stabilizers are again, those are again the stabilizers. So it would be W index T, and then cosets of those. Okay, so we found this group inside an affine space. So this is affine because the sigma, which is the Coxeter complex, is an affine space. And I'll show you another affine space containing this hexagon up here. So you've all seen this before. It's a tiling of the plane by equilateral triangles. And if you fix an origin and the two hyperplanes in here at an angle 60 degrees, what you see is exactly what we had up there, namely a finite reflection group generated by the two reflections S and T. And we have a third reflection R, so that the three of them generate us a affine, again, Coxeter group having this particular sigma. So it's R squared equals S squared equals T squared, and any pair xy to the power of 3 is 1 now, where x is different from y. Okay, so here's our fundamental domain of this action, and again, as in the other example, we label this by the identity. So any other maximal simplex in here is now labeled by an element of this affine, you can view it as a Weil group as well, affine Coxeter group, W. So if you do see it as a Weil group, and it pops up in this way, you can write this W as a semi-direct product. So this actually equals W0, semi-direct product, and lattice of translations. And these translations, they, in this picture, correspond to vertices all of the same color. So I start by coloring the vertices of our fundamental domain. And then I have this orange vertex, which is the origin, and anything that's in the orbit of this origin is also colored orange. So we've got a bunch of orange vertices. And then to see this semi-direct product, you can draw a hexagon around your origin. And you will see that the plane is not only tiled by the triangles, but also by the orbit of this hexagon. So you get this hexagonal tiling of your plane. And what you can easily see from this is that any triangle, which means any element in this affine group W has a unique decomposition as a translation, so pick an orange vertex, and locally a spherical direction, which is labeled by these guys here. Okay? So you can, from here, uniquely write this element as t to the lambda times some nu, where this is an element in W0 and the lambda, it's in the co-root lattice, or otherwise it's in T. Okay, so now I'm losing this thing here. Okay, I think it works. Okay, so we have this Coxeter complex, and what we want to do now is we want to look at sequences of maximal simplices, which are called alcoves in the following, in this complex. And these sequences, they're of a specific form, they're called galleries. So a gallery in such a sigma, and actually it doesn't depend on whether this sigma is affine or spherical. For the sake of this definition here, it works for both, is a sequence of alcoves, and this is just maximal simplices, such that subsequent ones are attached along a codimension 1 phase. Okay? So you have a sequence, Z0, maximal simplex, C1, another maximal simplex, C2, and so on. And what you put inside is a codimension 1 phase, so P1 is codimension 1 in both C0 and C1, and this holds in general, so you can put Pi in I minus 1 and I plus 1. Okay, so we glue in these things here, so here's some Pn sitting inside. Okay, to even add one more thing to this picture, let me show you a gallery. So you can start anywhere you like, say here, and I indicate this sequence by a trajectory which walks through the set of alcoves, namely maximal simplices that are in this gallery. And you see when you cross a line, this is the P that's recorded here. Okay? And the advantage of writing these P, they might seem superfluous at the beginning, is that in here you might repeat chambers. Okay, I've drawn a minimal example here, but what you also could do is you could start here, walk over, then come back and, I don't know, stop here, say. So it could be that one of these guys is equal to a later one, but it could also be that two subsequent ones are the same. And if that happens, like in this example, I come along here, and then I return to the exact same chamber, or alcove, I want to remember where I turned around, right? So these panels, they tell me where to turn around. So this remembers, Pi remembers where a folded gallery turns, and folded just means Ci equals Ci minus 1. Okay, so from this, the panels, they're colored. Okay, I colored the vertices in here, and with the coloring of the vertices, I can also color the panels, and I already did so with these orange hexagons. Namely, a color of a codimension 1 phase is exactly the color of the vertex it's missing. Okay? The codimension 1 phase is taking a maximal simplex, which has all the colors, so I delete one color and this is the color of my panel. So the orange ones have color orange, okay? And the colors, they correspond to reflections, namely R is exactly this orange color, S would be the white color here, and T, it's the other way around in the example up there might be. Sorry. So you can color them, and each color corresponds to a generator. So what it does is it gives you a word, right? So you can write the sequence of the colors of the PI, and this gives you a word in W, which is the sequence of colors in colors of the PI. And this word is called the type of this gallery, which I denote by gamma. Okay? So we have a bunch of things. We have galleries, which are these sequences. We know what it means that they're folded, namely they repeat a simplex somewhere. And we have a color attached to this gallery, right? So what we're going to do next is try to find, no, not one, I'm one step ahead. We're not yet ready to find things. We first need to know more about these foldings. Okay, so for now, these foldings can appear at random, but we want to have them more organized. So what I'm going to introduce is an orientation. Sorry? Orientation on this sigma, which will tell us when these folds are positive or negative. So they give them a direction. Okay, so what is an orientation? So this sigma, and let's stick to this example, it arose from, let me see how I did it, T on the right and S on the left, a finite reflection group together with another reflection R here. And an orientation is a choice of an element in this W naught. Okay, so how does it look like? Do I have yellow somewhere? Yes. Okay, orientation is the same as casting shadows. So the sun is shining a lot here, so if it comes from east in the morning, shadows go west and they turn around over the day. So if the sun is in a particular direction, which means we've picked an element in W0, and if this was the identity direction, we have here the sun chosen to equal our generator T. I can first of all orient half spaces of those hyperplanes, okay? So each of those hyperplanes here cuts my plane into two. And I call the side that contains the sun, that faces the sun, the positive side. Okay, so this is the positive side of this hyperplane because it contains the sun. The other side is called negative. Same here, this is going to be the positive side, this is the negative side. Same up here. And I continue putting orientations on parallel hyperplanes, the same manner I did for those three I started with. So also for this hyperplane here, the positive side is facing the sun, and so on. So you get a periodic orientation of all half spaces given to you by hyperplanes. Okay? And now we can say what we mean by a positive or negative fold. A fold, and remember, a fold was some Ci minus 1 equal to Ci in some gallery gamma is positive if this repeated chamber is contained in the positive half space at the wall spanned by their common panel Pi. Okay? And write it down is positive if in positive half space of HPi, which is nothing else but the span of this face Pi. Okay, let's draw a picture. Take a color. Let's start here and just do a gallery of length 3. So we have this simplex, then this simplex, and then this simplex again, and I touched the edge here, meaning that the panel that's in between the last and the second to last, the one before, second to last, is this panel here, okay? So the hyperplane spanned by this panel is this, and this repeated simplex, it's on the negative side, it's not facing the sun, okay? So this red guy would be negatively folded or not positively folded. Be careful, negatively folded is not the same as not being positively folded, because negatively folded is just replacing positive by negative in this definition here. So, but you can have, fold is either positive or negative, but if you look at the entire gallery, it could have positive folds, some of them, and also negative folds, okay? So a positive fold would look like this. Say, okay, this gallery consists only of 2 simplices. It's repeated along this. Codimension 1 says, and they're contained in the positive side of the span of the hyperplane. Okay, so a gallery gamma is positively folded. And now all this folding business only makes sense in an affine sigma if all of its folds are positive. So in particular, if there's no fold, then it's also positively folded. Okay? So, okay. Now we like to produce positively folded galleries. We need one more of these H tilde tilings. So what we're going to use is a tool probably well known to a lot of you. It's root operators by Gaussent and Petra Littelmann. So we pick an origin again, and well, we have the roots in here. Let's draw this first. Alpha 1. Alpha 2. And then for this example, I start with the minimal gallery. It runs from this alcove to this alcove here. So fix gamma, which is either positively folded, or if you don't know how a positively folded example looks like, in our example here it's minimal. Well, we've learned that things without any folds are positively folded, so this is good. We have gamma. Let's put an arrow here to see that it runs from here to here and not the other way around. Then there's root operators. E alpha and F alpha attached to each of these roots. And I'll show you what E alpha does to gamma. So E alpha, let's take E alpha 1. It picks the parallel class perpendicular to the root alpha 1. So we look at this parallel class of walls. And then it goes down as far as possible so that there's something on the other side. Okay, so we go up, down to here. And you fix anything up to here and reflect this last bit. So this gallery that now is folded along this wall or panel repeats its last alcove, and this is E alpha 1 of gamma. So if you do it another time, it's a little bit different. Then what happens is that you shift this fold to the next hyperplane in your parallel class. So this would be E alpha 1 squared of gamma. And after a while, it stops being defined, so you stop doing something. And then, okay, there's more ways to produce positively folded galleries, and this is why I put up the slides over there. I'll show you now in a bunch of slides more ways to produce positively folded galleries, and also how to manipulate them. So if you have a positively folded gallery, how you can obtain families of more positively folded galleries. So we're now in type B2. Do I have a change? We have our identity simplex over here. Again, as we saw in the beginning, all the maximal simplices, the triangles in those pictures, they're labeled by elements of the Weil group of type B2 tilde. So we have our fundamental domain, the identity here, and then the hyperplanes spanned by the codimension 1 faces of this identity, they generate the reflection group. So I fixed a minimal gallery, which is first this red piece here, then this blue piece here, and then this red piece here, from 1 to the identity, from the identity to this element A in our reflection group. And then this is not applying root operators, this is an explicit construction you can make. You can fold along the first hyperplane, which is this green one. Unfortunately, the color does not turn out so well. It's the first hyperplane in the parallel class of this one that's not through the origin, okay? So we fold here, meaning we reflect, it's almost like a root operator here. So we reflect like the rest of the gallery along this panel here. And then we keep going for this other parallel class here. So we get a second fold up here. And then another time folding along this green one here. It's parallel to one of the generators of the spherical Weil group. And then a second time also at this other hyperplane. So what we end up with is a gallery that's it's positively folded for the right choice of a sun, okay? So I didn't tell you where to put the sun here, but you can check with me that if we put the sun up here, that this gallery, well, it's negatively folded. If we put it down here, it's positively folded, okay? So all appearing folds are towards the sun. This is what the positively folded gallery is. Okay, so we have this thing. It depends on the choice of a presentation of the longest word in your spherical Weil group. Now, go back to type A. Here, it's the corresponding example in type A. So I fold this dotted gallery from the identity to A along this hyperplane here, and then on the other one, then again here. Here it's only 3 folds. I said it depends on the choice of the presentation of the longest word. In type B, you have length 4. In type A, you're of length 3, so you only see 3 folds here. So, okay, we constructed this little guy here. Next, let's play around with it, and you will see later that we're actually proving something here along the way. You can shift this little folded gallery to a point B, which is a translation in your co-root lattice. Okay, so pick a translation B that lives in the fundamental wire chamber and just transport your gallery there. What you can do now is you can elongate this gallery like we did on the right-hand side, so that if you unfold it again, it turns out to be a minimal gallery from the identity to X. And what we've obtained here is another positively folded gallery, now of a much longer type, namely type X, but it's also positively folded. Okay, so from a short positively folded gallery, we can make a long positively folded gallery. And now the root operators come into play. Here's our long positively folded gallery, the blue one on top. And now, as we did over here, we can push this fold using root operators downwards. And what we obtain is like a whole family of positively folded galleries. And the good thing is we know precisely where their end simplices lie. Okay, so we can control in which simplex they end. Okay, so I promised affine Deligne Lusztig varieties, so I should say something about them. So these pictures, they're contained in a paper by Goertz, Haynes, Coxeter, and Rumen. They ran, it's from 2010, I think, they ran computer experiment to compute non-emptiness and dimensions of affine Deligne Lusztig varieties. Now indexed by these pairs X and B. Why do I show here a picture of the apartment? It's a fact that for every B in G of F, there exists a B prime in your while group, which is sigma conjugate, and sigma is the Frobenius. It's 2B prime. And if two things are sigma conjugate, then the associated affine Deligne Lusztig varieties turn out to be isomorphic. So one can actually, if one wants to know about non-emptiness, for example, restrict to pairs X and B in your while group. Okay, so I'll come back to those pictures later. But in order to give you the precise definition of an affine Deligne Lusztig variety, we need some notation. Okay, we've already seen in the very beginning that we're looking at G over FQ bar of T. K, it's the algebraic closure, just to make notation shorter in the following. We have the Frobenius, and then we can extend this to the Laurent series with coefficients in K. And this Frobenius also extends to the Laurent series. We can look at the valuation of F, and as its ring of integers, obtain the power series. So the elements in here, they are for indices bigger or equal than 0. And with this, we can define the affine flag variety in which these affine Deligne Lusztig varieties live. So this is just a recollection of the affine flag variety. You have this group G, you fix a Borel and a torus. So this torus corresponds to this T here. So it's more or less the same T. And then you have inside the Iwahori subgroup, which in the associated Bruhat-Tits building is nothing but the stabilizer of your favorite maximal simplex in this one apartment we've been looking at here. So it's the stabilizer of the identity. Okay, and then we can define the affine Deligne Lusztig varieties. As I said, they're indexed by elements X and W, B in G of F, and they're given by this sigma conjugacy condition on the element B being contained in the double coset of X by my Iwahori subgroup I. Okay? So it resembles somewhat the classical Deligne Lusztig varieties, which are in G mod K, I think. And there, well, you just see more or less the same condition without the B. The B is due to the affineness here. Okay, so we have these objects, and the question we're interested in are the two most obvious ones you can think of. And in fact, they're not fully answered yet. So one wants, of course, to know when is such an affine Deligne Lusztig variety, which we can write down, actually non-empty, and if it's non-empty, what is its dimension? Okay, so we need to find pairs X and B in W times W because of this fact of things being isomorphic if they're sigma conjugate. And we want to compute the dimension of this variety. Okay, so previous results, almost all of them, they studied what's called the basic case, and I'll tell you in the next slide what basic means. There's all kinds of people having done work on this. Just to say a few names, it's Gertz, Haynes, Kottwitz, and Rumen, also the ones from which I've taken the pictures with all these gray colored alcoves on one of the previous slides. And he eventually proved non-emptiness pattern and dimensions for all the B's basic. And Young in 2014 also proved non-emptiness and dimension for X and B arbitrary. So where basic is a restriction on B, and then here this restriction was dropped, but only in the case of type A2 tilde. Okay, so apart from that, almost nothing is known. So what's basic? Basic means you're an element in your in G of F, and you can generalize the affine Weyl group. So as I said, this affine Weyl group is a semi-direct product of the spherical times the co-root lattice, T. Where instead of taking the co-root lattice, you can take the co-weight lattice. This is the extended affine Weyl group, and what it is, it gives you a cover with several layers or sheets, copies of this, of your affine Weyl group, and the number of sheets is the number of special vertices in your diagram. So if you see a diagram automorphism, each automorphism corresponds to another layer. Okay, so you can think of this as being the identity layer, and then whenever you can switch two things. So here you would see 3 layers because you can permute all the vertices. Okay, so and then being sigma conjugate to an element of length 0 means you're sigma conjugate to one of the covers of the identity. Okay, so they're all length 0. Okay, and just to give you an idea how much basic and non-basic things are covering, you see these blue vertices here, blue simplices here. They're all basic, and all the basic ones in this picture, because we're in the affine Weyl group and not in the extended affine Weyl group, they're all pairwise sigma conjugate. And then you see these translations in the dominant, so this black one should be the identity here. All the translations in this dominant Weyl chamber, they're not basic, the pink ones, and they're pairwise not sigma conjugate. So all the blue ones give you one isomorphism class of affine Deligne Lusztig varieties, while all the pink ones give you one each. Okay, so of course there's lots of white left. Yes. Sorry. Weyl sector, segment. Sigma. I'm sorry. Sigma is the Frobenius, so it takes you to the power of Q. Okay, and then you extend it to the Laurent series linearly. Okay, so we have this, and in the following we will focus on the pink ones. And okay, let me write down a conjecture how affine Deligne Lusztig varieties should behave for translations. And actually it's a simplified version of a conjecture for arbitrary B, which is terribly complicated. It's not that terribly complicated, but too complicated for me today here to state. And also I'm not going to say anything about it. So that's why I restrict to B being a translation, made by Gaussent, Coxeter, and Littelmann in 2010. So you have B being this in W. For such an element, there exists a natural number n, which depends on B, such that for all x's in W with length bigger than NB, and by length I mean the number of generators you need to write this, so elements in S as a product in S. One has XX of the identity being non-empty if and only if XX of B is non-empty, and if both are non-empty, then their dimensions are related. The dimension of XXB equals the dimension of XX of the identity minus rho evaluated against mu plus. So I won't tell you what those are. It's, yeah, never mind. There's a correction term that's easy to compute. And up to this correction factor, mu is the base point of your x, and mu plus its image under the spherical Weil group in the dominant Weil chamber. And yeah, okay. So we have this conjecture, and we want to see what we can say about it. Okay. So the point is, we restrict to these translations. So the pink things in the previous picture, and we do the following. We say that your affine Deligne Lusztig variety, parameterized by little x and b, is non-empty if and only if there exists a positively folded gallery from 1 to b of type x. So what does that mean? So remember, the type was the word you got from your codimension 1 panels in your gallery. And a gallery from 1 to b means just I start writing this word at the identity, do a bunch of folds in positive directions in some places, and then end up in the translated image of the identity simplex based at this translation B. Okay? So if I can manage to do so, this implies that this variety won't be empty. So this uses results of Gaussent, Coxeter, and Littelmann, which provided descriptions of XXB in terms of certain double coset intersections. And double coset intersections also appear in the work of Stefan and Peter, and also in alcove walk models of Parkinson, Ram, and Christopher. It's not the model, that's by them, but it's a paper on positively folded alcove walks, which also provides these double coset intersections. And with these, we can show that this equivalence holds. Okay, next, we prove, and you really, understanding this, you kind of get this for free. If you keep track of your folds and how you produce these positively folded galleries, you automatically see that this will encode you the dimension of this variety. You can compute it also in means of these combinatorics up here, namely by the number of positive folds and positive crossings. So what is a positive crossing? Here, this red gallery crossed this wall in its first step, so this is a crossing. And it's positive if you walk towards the sun, okay? And you only count those that are towards the sun and ignore the others. And using this number, you can compute the dimension. And again, it's based on the same combinatorics as above. And then, and we've already done this today, you construct and manipulate examples of positively folded galleries of a certain type that end in a certain translation B. Okay? So you reduce non-emptiness and dimensions to positively folded galleries. And with what I've shown you in the previous part of the talk, we can now start proving theorems. Okay? Okay, let's go back to this example. We've constructed this positively folded gallery that was of type A, right? So the word we produced walking along this minimal gallery was A. And then we folded gallery 1, 2, 3, 4 times. And then it becomes a gallery from the identity to the identity. Okay, the identity is a translation. It's a trivial translation. It has 4 folds and 1, 2, 3 positive crossings. Remember, the sun was down here. So the final 3 crossings of this gallery are positive. So what this implies is that, for one, this variety is non-empty. And on the other hand, its dimension is at least the sum of the positive folds plus the positive crossings. Okay, so I like to say that this gallery represents an element in this variety. Okay, okay, next example. We had this tiny one here, and as you can guess, it's non-emptiness of XA1 in the same fashion as the one on the previous slide. And now from there, we produce, like explicitly, we explicitly can construct this gallery. So we can explicitly construct, and I told you how, this gallery of type X that starts in the identity and ends in B. Okay, it's this blue simplex up here. So also this affine Deligne Lusztig variety is non-empty. And then if you would apply root operators, namely you walk from here to here and then to here, you would also see that this is non-empty, and this is what we did here, right? So applying the root operators, you see it's a whole family of non-empty affine Deligne Lusztig varieties sitting in between your type X up here, and the B's, so all those colors here, they sit in between this X up here and the identity below here. So all of them are non-empty at the same time. So it's actually even better than this conjecture guessed. Not only they're all related to XX1 being non-empty, it's the one at the bottom here, this black gallery, but they're also pairwise, it's equivalent, right? So whatever B and B prime you pick, non-emptiness is going to be equivalent, because they're all intertwined by the root operators. You can walk from one to the other, applying either F's or E's. So you get equivalence of all the non-emptiness. And then, okay, let's put this in a more formal form. So you take a translation B, and X be another element in your spherical Y group. So this will be the type of your gallery. And then you assume that B is in the convex hull of X and the base alcove. So this is exactly this picture here. You have this, and the convex hull of this gray one up there and the one down there is this region. It's like a diamond shape. Okay, so you're in this diamond shape, and then one can show that non-emptiness of the variety associated to X and 1 implies non-emptiness of X and B. And if they're non-empty at the same time, we can exactly prove this dimension formula that was conjectured over here. Okay. So down here, you may ignore this for now. It's the precise conditions you need on X and B for this to hold. Okay, let's go back to this picture. So what does this picture show? This picture is like in this conjecture here, you fix a B. And the B you fix is the identity. So the identity in this picture is this black alcove simplex over here. Okay, so you have this simplex. And then you color in other simplices. They're gray in this, bluish gray in this picture. And you color it in exactly if and only if the corresponding variety, x, xb is non-empty, okay? And these little numbers, which one can barely read, is the dimension of this variety, okay? So let's stare at things close to the origin for a moment. So this one here, well, you can easily find a gallery of length 2 containing the black one and this one with the number 1. So that one fold is enough to transport this end simplex to the black identity simplex, right? This is the proof of this variety being non-empty, okay? And you need one fold. This gives you a hint that the dimension could be 1. There's no crossing in this gallery. It only consists of a single fold. You take the gallery from the black one to its neighbor, and then you fold it, which means you just repeat the identity alcove along this codimension 1 face. And in the same fashion, it was computer experiments by these 4 authors who produced this picture, okay? And they also did a second case for another choice of B. So B now is this simplex over here. And well, you take a gallery from the identity to here and do nothing, right? It already ends in the correct B. So it shows non-emptiness of this variety. And of course, you didn't do any folds or crossings, so the dimension is 0. Well, it just contains a point. And it's for the neighboring one, it's the same argument as we did on the previous slide. You do a single fold and you get a dimension 1. Okay, and now I also have this jumping game. You can see a pattern if you squint your eyes a bit. The color changes and you can see a hole in the middle, but apart from that, those 2 pictures are the same. Okay, so let's explain this phenomenon. We start on the right-hand side, and we have xx1 being non-empty. So this is an alcove, this is a simplex in this picture. That's the last thing I'm going to explain. And we have non-emptiness, which means we have a positively folded gallery. Again, the sun is down here. It's called sigma, and it's blue in this picture, which shows that this guy is non-empty, okay? And then we translate this blue gallery to a different vertex. So, and we attach to it, we elongate the gallery at the beginning by this red bit. So what we do is we change its type by this red bit, and we also change its end simplex, namely exactly by this translation of this point here. It's this T mu on the left-hand side. So what we just proved is that non-emptiness of this implies non-emptiness of this. And you get a dimension bound by realizing that the dimension only can get bigger if you mess up with this red part in the beginning, because you may add positive crossings depending where the sun is, okay? So you see this theorem down here, non-emptiness is implied and there's a dimension bound implied, and this is exactly this phenomenon here. And because of the shift, you will see emptiness in everything that contains this red piece, okay? This is the hole that was appearing in. That's all I wanted to explain. Thank you.
Questions or comments?
So did you prove the non-emptiness for type B2 then?
We proved non-emptiness in all types and arbitrary dimensions for B, a translation. Like the theorems I showed you, they're type independent, and you just have these symmetries and patterns. In fact, we can do more, like if you see a symmetry of your diagram, whatever type it is, and you apply.
But you got all the alcoves for type B2, right? That was
no, not all alcoves, all translation alcoves. So, okay. The problem, so all our theorems, they're for B being a translation. And the reason is that we use things of those 4 authors that only work for translations. So far we cannot show you a theorem for another B, but it's current work, so we're trying to extend the results at the moment for arbitrary Bs. Let's hope that it will be finished soon. It's work in progress. But for now, we're restricting to B being a translation, but whenever you have this, you can show all kinds of symmetries using this combinatorics of the galleries that end in a translation, essentially. Yeah, thank you for the question, making this more clear.